Okay, so I guess we're officially up and ready to roll. Going to do two primary things, and one is to add the sort of the last quote unquote official piece to the statistical puzzle here, the piece that has to do with analyzing categorical data and kind of the parallel to t-test and regression, in that we're going to talk about chi-square and logistic regression. And you know, those elements are used quite often. You know, from time to time, you have to, you know, as we mentioned before, there's always a dilemma in knowing that your data was probably not randomly drawn. So, you know, you're dealing with non-random data, which makes it at best a quasi-experimental approach. But at the same time, there are ways in which you might want to deal with data if you take the pressure of causality out of it. In other words, if you're trying to you know, arrive at some conclusion about or some inference about causality, about cause and effect, then you've kind of put the pressure on what you can do. And by working with data that's categorical, we kind of take out the notion of causality, just as we do when we do a correlation or when we do regression. And so we kind of go with, you know, talking about probability and talking about predictability and all those sorts of things, and odds ratios, and just an entirely different type of language, as opposed to inferring causality and talking about causality. So sometimes it's just and I'll use this term inadvisedly. Sometimes it's a more valid way to approach things if you don't kind of worry about causality. Now, traditionally in social science research, we've always kind of wanted to get at that cause and effect thing. We've always wanted to know if one thing works better than another. So we've always wanted to do with, you know, sort of that comparative idea. But that's not necessarily the whole ball of wax, because we can know just as much if we're just looking for relationships and predictability as we can if we're dealing with causation. And so there's been a move in recent years, I'd say in the last 15, 20 years or so, as we've shifted gears and gone more to kind of thinking about relationships and thinking about predictability and you know, likelihoods and things that are more related to probability as opposed to causality. So that's a long-winded way of going about saying we're dealing with most of the categorical data. Yeah. Because we don't have continuous data, we can't have what are called parameters. Parameters are information that we know about groups if we have continuous data to work with. For example, a mean is a parameter. Standard deviation is a parameter. Standard error is a parameter. Standard error of difference is a parameter. And so, you know, those are the types of statistics that deal with those types of information, like t-test and like general linear model, ANOVA stuff, and multivariate stuff, and you know, all those sorts of things are considered to be parametric statistics because they deal with data around which you can have parameters. Well, obviously, if you're dealing with categorical data, you can't have average. You can't have a mean. because they're either in a group or another group. And so we don't have any way of generating parameters. So when we talk about dealing with categorical data, we call that type of analysis non-parametric. And so when you see the term parametric and non-parametric in an article or talk in a book talking about statistics, it just means that. I mean, if you see the term parametric, then you know you have an outcome variable that's probably continuous, at least one, if not more. And if you see the term non-parametric, then you know that most of your data is going to be, if not all of it, is going to be categorical. And it's just easier to get categorical data sometimes because you can draw the line and say, well, they're either in this group or that group, or they're on one side or the other. And it's very adept and easy to go to take continuous data and make it categorical. It's a whole lot more difficult to go back the other way. You can't generally take categorical data and somehow recode it into continuous data. But if you have continuous data, you can always recode it into categorical data. So it's just, you know, I've made a nice living dealing mostly with categorical data, simply because it provides more answers very often. And that's what people want in statistics, is they want the answer. They want to know, you know, how does this work? Okay. So yeah, that's kind of the introduction to the notion of things like chi-square and things like logistic regression. Yeah. There are probably, if not more, techniques in non-parametric analysis than there are in parametric analysis. But probably 95% of the time, there are only one of two techniques used, and that is chi-square and logistic regression. And so we're going to kind of do those and you know, stop there. And then for basically the month of April, we're going to look at articles and look at your work to kind of, you know, work it into a scenario that looks, you know, kind of something that we could do a statistical analysis on or a quantitative analysis on. So we'll kind of leave it at that point. Any questions or comments about any of that introduction before we roll forward? We're going to look on SPSS. I'm going to use as kind of the exemplar data file one we have used before a little bit, called adjunct file. This one's been you know, cleaned just a little bit, massaged just a little bit, so that we don't have a lot of strange data points in. But it does provide us the opportunity of dealing with real data that has a lot of categorical elements to it. So let me pull up my little thingy here. My little, slide y'all over here so I can see the whatchamacallit here. So far, we have kind of had the same form and formula in at least in form for all statistics. And you should be, you know, well aware of this now, is that, you know, we'll have, you know, comparative data on top and error term on bottom. And that'll generate some sort of statistic, whether it's an F for ANOVA, or whether it's a T for t-test, or you know, whether it's you know, different weighting for regression, there's always this formula somewhere in that that computational formula for those things. There's always going to be a comparison between comparative data and error. Well, we have to, in chi-square, we actually end up doing the same thing, but we come at it from a different direction. And let's say that we're wanting to know if there's a relationship between students that have participated in extracurricular activity, clubs, sports, things like that, versus kids that haven't. And if you go to any high school, you'll find that there's a certain split between kids that are have been in all kinds of activities and kids that haven't, that basically just come to school and do their thing and leave. Now, given the fact that we've lived in a strange world for the last year, this is a little bit of a strange example, but one that's workable. And let's just say we have as another piece of data, piece of information on students, whether they graduated or not. So we know two things on students. We know they participated in an extracurricular activity or not, and that they graduated or not. Well, just like ANOVA, one way of dealing with that is to think of that in a matrix. And we'll put the graduate up here, and yes and no. And we'll put the extracurricular over here, and yes and no. Now, let's say that we do understand, we do know a little bit more information. We know that 80% of the kids that enter high school, let's say in this particular school, graduate. And so we have 80% graduation, which means we have 20% don't. And we know by examination of overall numbers and rosters and things like that, that in a particular school we have, about 60% of the kids that participate in extracurricular activities and 40% of the kids that don't. And so we know that much information. And so if we, let's say we were going to look at 100 students, that we're going to randomly go pull 100 records of students, at the end of their 12th grade year, and look at those kids to see, that actually started in the 8th grade and graduated or didn't graduate by the time 4 years later. And so we can figure out what the likelihood of kids being in these boxes. We can figure out what we would expect to see in each of these boxes purely by chance. Well, another term for purely by chance is error. ERROR, error, random error. We can kind of equate those two notions. Random error also means purely by chance, random chance. And if we know the totals for these rows and the totals for these columns, we can figure out the expected value in each one of these purely by saying the expected value is equal to the row probability times the column probability. And so since we know the row and the column, we can figure out how many kids would be in that in each of those particular cells purely by chance, with nothing else occurring. And so we can think that, okay, for this one up here, we'll call this box 1 and 2 and 3 and 4. For 1, we know that 80% graduated, 0.8. Let's say we're looking at n of 100. N of 100. 80% graduated, and 60%, the road percentage, participated in athletics or clubs or whatever. So 0.8 times 0.6, 0.48 times 100, since we're going to look at a group of 100, we would expect to see 48 kids in here. Not 40, 48 kids. And if we went to box 2, we know that 20% didn't graduate, 60% were in extracurricular. 0.2 times 0.6 is 0.12 times 100 is, so we would expect to see 12 kids there. And if we go to box 3 down here in the corner, we'd say that 0.8 times 0.4, 0.32 times 100, so we'd expect to see 32 kids in here. And for box 4, 0.2 times 0.4, 0.08 times 100, and so we'd expect to see 8 kids in here. So if we pulled 100 records randomly of kids that had been in the school from the 8th grade and should have graduated 4 years later, we would have this outcome. We would expect 48 that graduated, that participated. We would expect 12 that didn't graduate, that participated. We would expect 32 that graduated and did not participate. And we would expect 8 that didn't participate and didn't graduate. And that's just probabilities, random chance. Let's say we go pull 100 records. We go pull 100 records. And so we're going to call that what we observed. And let's say that instead of 48 up here, we saw 60. And instead of 32 here, we saw 20. Instead of 12 here, we saw 8. And instead of 8 here, we saw 12. So now we have 2 pieces of data for each one of those 4 possible outcomes. We have what we expected to see versus what we actually observed. And so how do we know what we've got? Well, we've got, if we think about the formula up here, this comparative versus error, we've actually have, let's say for cell 1, we have to do it cell by cell. We can't do it for the entire matrix. We have to do it cell by cell. For cell 1, we actually observed 60. So let's say we observed minus what we had expected, divided by what we expected. Remember, expected is random chance is the same thing as random error. And so for cell 1, we observed 60. We expected 48. And our error would be 48 because that's what we expected. Now, there is a problem in thinking this through, and it's a computational problem. Because if we expect 100 and we actually observe 100, guess what happens when we add all these differences up? It becomes 0. And so we have to square the top of this to get rid of the 0. And for cell 1, that becomes 12 squared, 144, 144 divided by 48. Okay. Now we have to do it cell by cell. So for cell 2, it becomes observed of 8 minus expected of 12 squared divided by 8. Oh, excuse me, divided by 12. And so this becomes then 16 divided by 12. Now we're summing it all, so we're adding these things together. And for cell 3, got to get my color straight here. For cell 3, we have 20 minus 32 squared divided by 32. So this becomes minus 12 squared, 144 divided by 32. And then for the last cell, it becomes 12 minus 8 squared divided by 8. And so this is 4 squared, 16 divided by 8. Well, at least one of them is simple. This is 2. On my handy dandy phone here. So 144 divided by 48 is equal to 3. Uh, 16 divided by 12 is 1.33. And 144 divided by 32, I should know that right off the top of my head. I should be able to do that, but I've gotten old and slow, is 4.5. So we have 2, 5, 9.5, 10.5, 10.83. So 10.83. And the degrees of freedom for that chi-square are rows minus 1 plus columns minus 1. Or is it times 1? I have to look that up. I think it's times 1. So the degrees of freedom for this is 1. Rows minus 1, 2 minus 1 is 1. Columns 2 minus 1 is 1. Squared, or no, times each other. Degrees of freedom is 1. Now, that would be a significant outcome, I can tell you. Because anything above about a 2.86 chi-square, and this particular stat is chi-square. And so what it does, it gives you a way of taking categorical data using pure probability to turn that into a statistic which has a distribution which becomes predictable based on degrees of freedom. And so what we did is we didn't abandon our logic. We just used some, logic thought manipulation to arrive at something that gets us back to our original logic, where we have a statistic that has a predictable description or predictable outcome, and we can understand the probability of a particular value of chi-square. Yeah. You never have to do this in real life. It's easy enough to do, though. I mean, this is the type of stuff that, if you were, caught without computer or cell phone or iPad or anything except a stick and dirt, you could still do it. Because the way of developing this from a pure probability model into a distribution model is insanely simple. Questions? All righty. Let's go do an example. Now, this adjunct file is up on your As You Learn. I just stuck the clean version up there, so there should be a link to it. But if and when you do that, let me see. You should get a data file that looks something like, if I can get my Zoom stuff off of it. There it is. You get a data file that looks like this. And if you remember the data that's in here, there's a lot of demographic data. There's continuous data for grade points and continuous data for standard outcomes, and then some categorical data for graduation or not, and being in developmental ed or not, and lots of different types of data. And this is the real type of data that you would deal with from a student information system, from a college or a university. And so once you get kind of to this point, then you can begin to do some analysis based on thinking of categorical data. And so let's do one that's fairly straightforward. It is a categorical approach. And so we need to deal with categorical data. Now, as it turns out, the categorical data can have more than 2 levels. For chi-square, it can have as many levels as you want to, as long as you have most of the cells filled, or the cells filled. But we'll pick one that only has 2 levels, and we'll pick part-time, full-time, which is this status for semester 1. And we'll pick we'll pick male, female. We'll pick gender, male, female, which is over here. And so we could ask the question, is there a relationship between gender and whether an individual is part-time or full-time? And that might be a useful question to know, useful piece of information, depending on what's going on at the college. And so for these types of analysis, we have to start with a matrix. We have to start with the matrix, and in SPSS, a matrix is called it's in descriptive statistics, and it's called a crosstab. And so now we have a crosstab. In the rows, we'll put sex just because it's there. And in the columns, we'll put status. That's the part-time full thing, just because it's there. Statistics, we'll run a chi-square. We'll select chi-square as the statistics we want to run. There are others, but we want to run chi-square. In each of the cells, you have to tell it what information you want in the cells to display. I'm going to have it to display the expected and the observed. Now you can do that as percentages if you want to. I always like to kind of look at the raw numbers because I think it's an easier, it's an easier interpretation if you look at raw numbers as opposed to percents in this notion. And so we will continue, and okay. Now I'll stop the share and go over and share the output file. Let's slide this over a little bit. All right. And so, here's basically the script file. We did tables, status by sex, format, value tables, chi-square, cell count includes expected. It's going to include the observed, and then it's going to round the cells off to a tenth or so. And so we have here a count, full-time and part-time in the columns, FT and PT, and female and male in the rows. Now, notice we didn't even have to recode it to numbers. We can use alphanumerics when you're doing chi-square. And so for each of those cells, for the full-time females, we expected 154. We got 140. For part-time females, we expected 400.7. We got 415. And for males, we expected 121. Full-time, we got 136. And for part-time, we expected 316. We got 302.
Where do you get the expected count from?
For the table here, it figures out the totals for the rows and the columns, and computes them just like we did with the cells on our little freehand example. For example, it figured out that the the percentage for females was a certain percentage, the percentage for males was a certain percentage, the percentage for full-time was a certain percentage for part-time was a certain percentage, and then it goes cell by cell and multiplies those percentages together and then multiplies it by the total number of subjects in the whole table. And so it just calculates it the same way I did. And that's why you get the 0.7s and things like that, because it will not necessarily always come out even when you do it that way. But if you look, you've got here 0.3, 154.3 and 400.7. Well, there's always going to be, that's always going to add up to an even outcome, and that adds up to 555. And when you go down here, it's a 0.7 here for expected count, and it's a 0.3, and so that adds up to an even number. So basically, it takes a look at what's in the table in terms of the number of females, the number of males, what percentage that is of the total, the percent of full-time, percent of part-time, what percentage that is of the total, and it calculates what would be a randomly expected outcome. And so without knowing that data, it can calculate from what's in the table. But it does the row and the column, or the row and the column calculations before it does the chi-square calculations. Is that okay? You got that? That makes sense. Yeah. Not a bad question, because there's always someone always asks that and say, well, how can they be a 0.3 of a person? Well, they can't. And so it's just a mathematical outcome. And the chi-square test is just below that. Pearson chi-square, we deal with the first line, Pearson chi-square, and we get a 0.04, so it is significant. It's a significant outcome. We can look at what are called likelihood ratios, and that's kind of like what's the likelihood of being in any one of those columns, and kind of what's the average over that. The Fisher's exact test will give us something that's pretty close, but 0.25, but it assumes that we have randomly occurring data, and so that's why we don't look at that. We always look at Pearson chi-square. So it's a significant relationship. Now, how do we interpret that? We say that there is a significant relationship between gender and whether a student that first semester is full-time or part-time. And then when we go back and look here, we find out that females, we expected more full-timers than we got. And we expected fewer part-timers than we got. And for males, we expected fewer males as full-timers than we got. And we expected more males as part-timers than we got. So if you kind of think those things through, basically there's a significant relationship here. And the nature of the relationship is that males are more likely to be full-time than we had anticipated, and females are more likely to be part-time than we anticipated.
Can I go back to the percentages?
Mm-hmm.
So in your example, you were saying for the graduates and extracurricular that you did on paper, you had like some expected percentages of 60% and 40%.
Yeah, we knew what that percentage was. Yeah.
How do you know that here in this example?
You don't. It's calculated purely from the data in this table.
So if you're calculating expected from the data in the table and you're calculating the observed, That's the part I've never understood about chi-square.
Okay, well, let me say it this way, okay. And then we'll do it on the pad here in a second, and just to show you that. In fact, let me rerun this with percentages. Okay, let me rerun this with percentages.
So I have an example that I taught when I taught biology, and we used chi-square to look at when you have a Punnett square on paper, you can work out, how many you have a corn Indian. Well, that's probably improper to say. The corn that has the multiple colors, you have that, and you can calculate on paper what you expect to have, like so many yellow kernels, so many purple kernels.
Right.
And then we actually count the kernels.
Right.
And record that, and we can look at a chi-square to see if there was a significant difference based on what we expected from what we worked out through Mendelian genetics and the Punnett square on paper versus what we observed. So I get that, but in this data set, where are you getting the how do you know what your expected is should be? You don't have like Mendelian genetics, theory to work off of.
No, but you have real data. And so let's just look at this chart for a second. Okay, we know that within sex, we know that there are 25%, we'll round 25% full-timers and 75% part-timers. 25 and 75. We've got that right here. Okay.
Mm-hmm.
We also know that the way it divides out full-time, part-time, let's see, this data is always, this is the reason I don't like to do necessarily that example, but let me see if I can print this off real quick. And where's my file button? There it is. File, print. Okay. Now, if there's any ink in my printer. It's maintenance, so it's grinding. But in terms of known values, like you have to think about where known values come from. Known values come from real data. Over a period of, say, years, over a period of 4 or 5 years, you know that in the example we did on paper, you know that 60% of people participated in extracurricular. You got actual numbers for that. And so you know that 40% didn't. And you know that from 8th to 12th grade in any particular class, 80% of them graduate, which means you know that 20% didn't. But where does that 80 and 20 come from? It comes from real data. It comes from actual recorded data. And once this thing cranks over here, I guess I haven't printed anything today. But think about this being a snapshot as opposed to a 5-year trend. This table is just one snapshot. And so let me stop here and go over to my little thingamabob. And share that. I'm going to blow this up so we get a better look at it. I guess I have to do that before we share it. I got to blow it up first. Well, it's not working. I'm having a hell of a time with this thing. That's not it. Well, we'll just work off of this. That won't work. That'd be too much. Let me find that thing again. What do I do with it? Okay. Share recording. Oh. I guess I must have closed it out. Let me reopen it. Okay. Okay, there we go. All right, now I'm going to share it and we can play with it a little bit. Okay, so I'll have to just move it across the screen a little bit, but that's fine. So here is that crosstab with additional information in that we've gotten, these percentages down here, okay? We know the total number of cases. If you come all the way down here to the count down here, we know that there's 993 cases. So we'll record that. We know that within, if we look at the columns, we have totals per columns. Full-time, part-time, we have 27.8% full-time and 72.2% part-time. So we know that. And if we then go and look at within gender, totals over here, total would be over here, wouldn't it? Okay. We've got all right, well, let's just deal with, we'll deal with the count. That's easier to deal with. So we know that we have for full-timers, we know that we have 276. For part-timers, we know that we have 717. And if we do the math based on 993, we'll get these percentages. In other words, if we divide these ends by the overall end, we'll get these percentages. Okay. We know we have 555 females right up here. And for males, we know that we have 438 right here. And so let's look for, if we do these percentages, trying to figure out where we got these percentages at. They should show within a table somewhere. I guess I need to lay them out the other way to get the table, but we can do that real quick. 555, 555 divided by 993 is equal to 55%, 55, or actually 56% if we round it off. And so this will be 44%. So if we wanted to know, let's say we wanted to know full-time female, percentage for full-time female. We would know that there's 56% female and that there's say 28% roughly full-time. And so do the math, 0.28 times 0.56 is equal to 0.1568. 0.1568, and we have 993, so that times 993 is equal to 155.7. So we should have full-time female expected value of 155.7. If we go into the output file, which is here, and we go back up to this earlier version we had up here without all the percentages. Full-time female, it's 154.3, but I guess I'm off ever so slightly with the rounding stuff. You know, I rounded it off roughly, and I got 155.7, it's got 154.3. And that's purely a rounding error on my part. And so you can get each one of these expected values from the actual numbers the same way. So it's calculated from this set of data. Does that help? Okay, I know I botched that a little bit. Made it overly complicated.
Yeah, if you were doing a study that, you know, you knew, like in the other example, over 10 years, you know, 60% are male or female, 40% are male, you don't need to input that into SPSS, or do you? Is there,
No,
is there ever a time that you put those parameters into your chi-square?
No, never.
Okay.
Yeah. Never, because you know, whatever the data set is, I mean, if you've got data from 5 years, you just put all that data in there. And it would, you know, calculate the trend over 5 years for the expected value automatically. If you have just one set of data, then it works from that existing set of data. And so it's going to be accurate for that existing set of data. So it's whatever data you got in there, whether it's 1 year, 10 years, 5 years, it will automatically, you know, make the adjustment or the calculation for that. Yeah. Okay. All right. And so, as I said, then we can gotta kind of go in. I like working from here because I think the raw numbers show the variation really quickly. You can get the same outcome from over here because you're going to have an expected value, and then you're going to have, you know, kind of an outcome, exact outcome value. I mean, these percentages come from these actual numbers. I mean, I just think it's kind of fuzzy. You know, I really have some difficulty sometimes kind of sorting through them. I like it better when I can just see the raw numbers. And then you have less data that you have to, you know, kind of think through and work through. That's just my preference over time, is just to do it that way. So the outcome here would be that there is a relationship between gender and full-time, part-time status during the first semester. And the nature of the relationship is that females are less likely to be full-time than we had expected, and males are more likely to be full-time than we expected. So if you interpret one column, then you've automatically interpreted the other column. But you could approach it from either direction depending on the type of question you're asking. Okay, any other thoughts, questions about that? Beyond, God, why did he bring this up? Okay. I'm going to take a real quick little break here because we really need to deal with this in sort of, you can't readily roll right into logistic regression from chi-square. I mean, you have to kind of set up some other parameters, some other, not parameters, but some other, givens when you're dealing with logistic regression. And so I'm going to take about a 10-minute break so I can stop this recording and let it begin processing. And I'll be back in, 4:30? I'll be back at say 4:40. 4:40-ish, 4:40, whatever. And then we'll get into logistic regression because it provides a way of doing lots of very useful stuff, one of which is predicted outcomes. And so we'll kind of stop there and